Okay, so today we will see this frame problem, how the frame problem can be solved using SAP. I hope the screen is visible to everybody. Can you see the problem statement? Somebody please respond.
No, sir.
Yes, sir.
Yes, sir.
Okay.
Yes.
Okay, fine. So this was the same problem I'm taking, which is covered in the theory class. Okay, so it's a simple frame. It is having two columns. One is 6 meter height, second one is 4 meter height, and there is a simple beam which is resting on this, and the loading is already shown in the figure. In the numerical, the value of area of cross section of beam and the moment of inertia was given. So the area was given to you as something like 0.06 meter square. So I have solved this in terms of B. So the B comes out to be 0.06 divided by D, and the moment of inertia, which is generally expressed by BD cube by 12. So the value was given to you as 0.00045 millimeter to the power 4. So if I solve this, so I'll multiply this 12 with this. So BD cube comes out to be 0.0045. And if I replace the value of B with the value of 0.06 by D, so it becomes something like this. So 1D will get cancelled. So it becomes 0.06 into D square equals to this value. And it gives you the value of D square as 0.09. And the capital D comes out to be 0.3 meters. Okay. So once the value of capital D is calculated, you can substitute it in this particular expression. So you can get the value of B as 0.2 meters. Okay. So we will be solving the same problem with the dimensions now. So B I'll be taking 0.2 and the D value I'll be taking as 0.3 meters. Okay. The value of moment, the modulus of elasticity is already given to you. That is 1.5 into 10 to the power 7 kilonewtons per meter square. Okay, so let me open the SAP now. So this is the SAP educational version. So on the bottom side, you can see the units are kilonewtons and meters. So please check before drawing whether all the units are correct or not. So if you refer the problem statement, everything is in meters as far as distance is concerned, and as far as forces are concerned, everything is in kilonewtons. Okay, so if I want to draw this in X and Z plane, so X being horizontal and Z being vertical, so I'll be needing a grid in the horizontal distance. The horizontal distance is 6 meters, so I'll be needing a grid of 6 meters in the horizontal direction, and in the vertical direction I'll be also needing the grid of 6 meters. Okay, I'm keeping the interval as, let us say, 1 meter each. Okay, so I'm going for a new file. Okay, so this is my new file. So in the X direction I want to have 6 meters. Y direction I won't be requiring because I'll be working in X and Z plane. So in the Z direction it will be 6 meters, and the distance between the grid line spacing is already 1 meter each. So this is going to solve my purpose. So you can see, let me close this window, and if I go in XZ view, so this horizontal direction is X and the vertical direction is your Z. Okay, so you can see there is a grid of 6 meters, 1 meter by 1 meter. The maximum distance in the horizontal direction covered is 6 meters, and in the vertical direction the maximum distance covered is 6 meters. Okay, so let me save the file. So while saving the file, please ensure that you are using a simple path, and the folder names and file names, they should be less than 8 characters because this is the older version, so it doesn't support the long file path. Okay, so I'll be saying FRAME frame 1. Okay, so I am saving this into a C drive SAP, so small path and frame 1. Okay, so I have saved this file. Okay, so now the first thing I have to do is define the material. Okay, so if you refer the problem statement, the modulus of elasticity is considered as 1.5 into 10 to the power 7 kilonewtons per meter square. Okay, so here I will go to the define. I'll say material. So let us say this is concrete. I'm going to modify the property of the concrete. So here I have already written. So let me write it once again. So this is 1.5 into 10 to the power 7. So it is written as 1.5 E7. Okay, I am not changing any other parameter as far as this material properties are concerned. Okay, so let me save this. So it is saved in concrete. So whenever I am defining the material properties, I'll be using the concrete now. Okay, then the second is your B and D. So we have just now calculated the depth of the section should be 0.3 and the width of the section should be 0.2. Okay, so here I'm going to define the frame section now. So this is frame section 1 is already there. So I'm going to modify this. So the depth will be 0.3 and the width will be, let us say, 0.2. Okay, but here it is not made up of steel, it is made up of concrete, and we have already changed the value of modulus of elasticity of the concrete. Okay, so let me save this. So okay, so now what I have done is I have defined the material, then I have defined the frame section, then I have to remove the self weight. So to remove the self weight, you go to the static load case and there is a self weight multiplier, you change it to 0. I'm saying change it to 0, don't press OK directly, you have to first change it. So once you change this, this 1 will be changed to 0. So now you can see this is changed to 0. So now self weight factor is 0 and then you press OK. So let me save the file once again. So I have defined the frame sections, material as well as the self weight. Okay, so now I have to draw this. So while drawing this, so if you refer this particular problem, so I'm considering this as node number 1, this as node number 2, this is node number 3, and this is node number 4. Okay, so let me draw it in a straight way. So I'll go for add draw frame element. So from here to 6 meters I have one frame element, then from here to here I have another frame element, and from here to here only 4 meter I have another frame element. Okay, so now I have, this is section 1, section 2 and section 3. So I'm selecting all the section and then I'm going to assign the frame section to the this frames. Okay, so I'm going to assign frame section. We have only one frame section, that is F frame section 1, FACT 1. So I'm going to assign this. So as soon as I press assign key, you can see FACT 1 is reflected just next to the section. Okay, then if you refer the problem, we have a fixed support over here, that is at node number 1 and at node number 4. So I am selecting both the nodes. I am selecting this node, I am selecting this node, and then I am selecting this support. So here there is a fixed support option over here. So fixed support option, what it does, it is not allowing you for translation in any of the direction, as well as the rotation is also restrained. Okay, so once I press this OK, you can see fixed support is assigned on both the joints. Okay, now comes the tricky part, that is the loading part. Okay, let me save the file once again. So if you refer the problem, you will find there is a uniformly distributed load of 40 kilonewton per meter at the topmost beam. Okay, so I am selecting this beam. Okay, so once I select this beam, this icon is getting highlighted, that is assign frame span loading. So once I click this, you will get a dialog box. Now here there is an option of uniform load. So if you refer the problem, the uniform loading is 40 kilonewton per meter. So I'm just going to put 40 over here. And if you see the direction of the load, it is in the direction of the gravity. Okay, so in the SAP, the direction of gravity is by default minus Z direction. Okay, so Z is vertical direction, so minus Z will be your default gravity. If you want, you can change this to minus Z also if it is required. Okay, anyway, so I'll put it in the direction of the gravity. So once I press OK, so what you will find, the 40 kilonewton load or 40 kilonewton UDL is applied throughout the span of this particular beam. Okay, now if you refer this problem, so there is a 100 kilonewton load which is acting at a distance of 4 meter from the bottom. Okay, so I'll go back to the SAP. So from here to here, so remember when I have drawn this particular frame structure, I have clicked over here and then I have clicked over here. So this is my starting point and this is my ending point. Okay, so the distance is always measured from the starting point. So I want to have a load over here. So this point is located at a distance of 4 meters from the starting point. Okay, so I'm going to select this. Okay, so again I'm choosing the same option, that is assign frame span loading. So now here you see earlier we have given 40, so uniformly distributed load is still there. So first thing what you have to do is you have to make it to 0. Okay, then secondly, I want to have a load which is acting at a distance of 4 meter. So now we are talking about the absolute distance. So first of all, I need to change this to absolute distance. Okay, So I want to have a load which is at a distance of 4 meter. So I'm just going to put 4 meter over here. Okay. And the loading is there. The magnitude of the load is 100 kilonewton. Okay. Now you see the by default, the direction of the loading is gravity. So gravity means minus z direction. But I want to have the direction of the loading in the positive x-axis, and this x-axis is nothing but your global x-axis. Okay. So I'm going to select this one, and I'm going to select the global x-axis. So now what it is going to do, it is going to apply a load of 100 kilonewton at a distance of 4 meters from the starting point. So this is your starting point. So 4 meter will come over here in the direction of global x-axis. So in the global x-axis, you can see it is reflected over here. Okay. So once I say okay, so you will find the 100 kilonewton load is acting over here. Okay. Now similarly, you have to apply 80 kilonewton load, which is exactly acting at a center of this particular beam. Okay. So now I'm selecting this particular structure. Okay. This column, I'm selecting this icon once again. So now here you see everything is already given. So because we have given 100 kilonewton load at a distance of 4 meters. So now it is at a distance of 2 meters. Okay. So here I'm just going to put 2 meters. And if you refer the magnitude, so magnitude is 80 kilonewton. Okay, so this is 80 kilonewton. So you see at a distance of 2 meters from the top. Okay, why I am saying top? Because when I have drawn this particular frame structure, while drawing this particular member, this was my starting point and this was my ending point. So it will measure a distance from this starting point. So it is acting at a distance of 2 meter. The magnitude of load is 80, and it is acting in the direction of the global x-axis. That is, from this point it will be acting like this. Okay. So once I say okay, so you'll find the 80 kilonewton load is perfectly applied over here, right? So now you see this 100 kilonewton load is applied, 40 kilonewton UDL is also applied, and 80 kilonewton load is also applied correctly. So let me save the file once again. Then now we have to solve this. So if you solve this, first of all, you have to select the set option. So in the select set option, you will find there is a plane frame structure over here. It is there in X and Z plane. Okay. So remember, we have also drawn a structure which is there in X and Z plane. So I'm just selecting this. So once you select this, what will happen? The degree of freedom in X direction, in the Z direction, and rotation about Y axis, now it is permitted. Rest of the thing is not permitted. Okay. So let me say okay. So the set options are already done. Let me save the file once again, and then I'm going for analysis. Okay. So if my input is correct, so analysis will be done correctly. So fortunately input is correct. So you can see the analysis is completed. And once I say okay, I can see the deform shape over here. Okay. So let me just reduce the scale slightly. If you want to have, let us say, the support reactions, so you can say joint reaction. So you can see the reactions are there like this. So this is 138 and vertical is 136, and here it is 41.47, and here it is 103.7. Okay. Then if you want to know what is the bending moment diagram, so bending moment diagram, you have to go for moment 33. You just unselect this field diagram and you can see the show values. So if you refer your notes, you will find all the values, they are exactly matching. This value, if you refer the note, it is 106, and this value is also 155, and this value is also 239. Okay. So this is about the shear force. Also, this is the bending moment diagram. So if you want to have the shear force diagram, you select this F, and you can say shear 22. Okay. So once you select this, so you will find there is a shear force diagram which is displayed on the screen. Okay. So let me save the file, and let us say I want to have the output in a proper format. So I'm going to file, print output tables. So here I'm just clicking the reactions also, because I am interested in reactions also, and then say print to a file. So the file name will be C sap and frame1.txt. Okay. So I'm saying okay. So this file will be saved over there. So let me open the C drive. So this is my C drive, and in the C drive I have SAP, and the first file you will see, because this is the latest file which is created. So frame1.txt is there in front of you now. Okay. So here you see the first and the fourth joint was the fixed joint. Okay, so you won't find there is any displacement either in XYZ direction or the rotation in XYZ direction. Okay, this is your second joint. Okay, so if you refer the second joint, this particular joint is nothing but your this is your second joint. So at the second joint you will find, so this is the displacement in X direction. Okay, so you can refer your notes. I'm sure that you are getting the same answer. So this is the by default unit is meters. So the displacement of this joint is 0.0818 meters in the positive x-axis, and as far as the displacement in z direction is concerned, that is the vertical direction, so it is very negligible. So it is 6.9 into 10 to the power 4 meters. But as far as rotation is concerned, so rotation is about the y-axis. So here R2 you will find this is the value, that is 0.0134. This is the rotation, and the rotation here over here is what, degrees or radians. So mostly it is radians over here. Okay, so you can check these values with your solved problem in the class. Similarly, this is the third joint. Okay, so third joint is also showing a displacement in X direction, also showing displacement in Z direction, and there is a minor value of rotation also at the second joint. Okay, as far as joint reaction is concerned, we have already seen there are two joints, joint 1 and joint 4. So the values are there on the screen as well as in the output file also. And here, this is the most important part. Here there are three frame section: frame section 1, frame section 2, and frame section 3. This M3, this particular column denotes the bending moment. Okay, so on the frame section 1, or the first vertical member, you will have the 106 at the bottom and 57 at the top. So if you refer this value, so you will see 106 is there at the bottom and 57 is there at the top. Okay, the second is the horizontal member, so it will be minus 57 to minus 155. So we can see this value will be minus 57 and this will be minus 155. Similarly, this value will be minus 155 to plus 239. So you can see these values are there in front of you. Okay, so I'm sure you will be getting the same answers when you solve this particular problem. Okay, so please everybody try this problem and show me on the screen whether you are getting it correctly or not. Okay, please do this. And do you have any queries? Please let me know. Yes, please let me know. Any queries are there? I'm guessing there are no queries, so please start working on the problem and please show me the screen. Okay, and I think all 18 students are present, so I'm marking all students at present. Okay.